Hello everyone, welcome to the Electromechanical Devices course. In today's lecture, we're going to continue the topic that we started the previous meeting, which is regarding the chapter 3. As we said that chapter 3 covered the capacitance and inductance. It means that we are interested to understand these two physical phenomena and the function of the capacitors and inductors and how they would do control of the current or the voltage through the electrical circuit. And this is what we already introduced to or discussed the previous meeting. As we said that the resistor, the capacitors, inductors, these are different types of controllers that they give us the ability to control the amount of current or the amount of voltage at a certain location or over a certain element within the electrical circuit. And in the previous meeting, we started the capacitors and capacitance to talk about the capacitance in general. And so today we're going to continue, but I'm going to give you a very quick summary of the different formulas or laws that we already discussed in the previous meeting. We said that for the case that we have capacitor, for the capacitor, that the charge over the capacitor is equal to the C, which is the capacitance, which is the constant or a material property of this capacitance or capacitor. This capacitance C, it is measured in farad, and which is equivalent to coulombs divided by volt, times the voltage, which is the voltage over the capacitor itself. So as you can see, we do have a direct relation between the charge and the voltage over a capacitor, but which is very similar to the thing that we said for the resistor. The resistor is proportionally related to the volt, but or the resistor gives a proportional relation between the current and the volt, but the capacitor gives proportional relation between the charge and the volt. Here the relation is proportional relation between the charge and the volt, which is somehow different than the current, but the current, it can be related to the derivative of the volt through the capacitor. It means that the current equals the capacitance times dV by dt, which is the derivative of the voltage over time. And we said that in case that we do have the volt is constant like DC volt, so the capacitor in this way it will be open circuit. It means that it will have the current definitely will be zero because there is no time derivative for the volt with respect to the time. And if we decided, if we are interested in the voltage should be 1 over C, the integration from T0 to T, the I of T dt plus V0, where V0, this is like the initial charge. This is like the initial energy or the initial voltage that is already stored in the capacitor. And then we are going to charge more. We are going to add more voltage, which comes through the integration of the current over the time. It means that we can send a pulse of current over a certain period of time. The integration of this current over the time, this is going to give us another volt over the capacitor. So it is clearly seen that the current is related to the voltage with different relation than the one that we used to see for the resistor. Here it depends on either the integration or the derivative of the volt and the current. How about the power? We still gonna use the same formula. Like for the power, the electrical power, it is commonly known as the volt times the current. So your objective is just to come up with the current or the volt using these formulas and plug them together or multiply them together. You're gonna end up with the power. Very simple. The energy, it should be the integration of the power over time, which is just the conventional formula. This is the classical formula and even the same formula that we use with the resistors. But if we plug with the power here, we're going to end up with VI. And if we substitute with these two expressions here, we're going to end up with this expression for the power, for the energy over a certain period of time that it should be stored within the capacitor. As we discussed the previous meeting, that the capacitor, it works like a store. It means that we are delivering energy, we are delivering electrical power to this capacitor. This capacitor is going to take this energy and store this energy for a while. So the amount of energy stored by the capacitor, these are the formulas that would be used for calculating the energy stored by the capacitor. Then we can make use of this stored energy after a while to operate the another electrical element. Then we discussed these formulas. We practiced this formula through this example here too, and through this example we were interested in calculating the charge and the current over how they are changing through the capacitor, how they are changing over time. And we definitely use these two formulas. We use the Q equals C times V, and I equals C plus dV by dt. And we got the V, which is the voltage, over the capacitor, which should be the same volt as the battery. Your objective is just to solve the Kirchhoff voltage law to this circuit and come up with this VC. Then if you plug into this equation, so the key idea is to come up with the formula or the equations of this discrete function. This is a discrete function. It is changing. Here it is a linear straight function with increasing rate. Then we do have a constant line or a constant function. Then we do have another function with a decreasing rate. So your objective is just to come up with these different functions of the discrete system or this discrete function or equation, and you do some derivative or multiply times C, you're going to end up with functions for the current and the charge, and then you can simply plot these the current and the charge as we presented in the previous meeting. So today I'm going to give you another example, which is a very similar example. Then we're going to move into discussing the equivalent capacitors. As we discussed in the resistor, if in case that we have multiple resistors, we can combine them into one into one resistor. This resistor should be equivalent to all of these multiple resistors. We're gonna do the same for the capacitors. Then if we do have time in another video, we're gonna move and repeat the same but for the inductors. All right, so now let us focus on the capacitors or the capacitance, and let us consider this example too, that state that suppose that the voltage waveform shown in the figure is applied to 10 microfarad capacitance. So this is the volt that it should be applied. So this joint that I'm gonna present here is not given, but this is what you should understand, that we already have a capacitor somehow. And this capacitor, there is a volt between the two ends of this capacitor. The volt of this between these two ends is V of t, which is already given in this graph. So this is the representation or the time variation of this voltage over the capacitor with the capacitance C. C is given by 10 microfarad as already mentioned there. And if you remember, the micro, it is the multiplication of 10 power to the power -6 farad. So this is the equivalent one. If we decided to get rid of the micro, find and plot. It is just not just find, also you are required to plot the current. If I ask you just to find, there is no need to plot. It is required to find and plot the current, the power, and the energy stored for the time between 0 to 5 seconds, within the time period which is from 0, 1 up to 5 seconds. And the time is already given in second, and the voltage is already given in volts as already represented here. Make sense? So how we can solve this problem? We're gonna do the same. It is required to find the current, which is I of t, and the power, which is P of t, and then you are required to find the energy, which it should be the W of t. And the energy, it is the integration of the power. So if we got the power, we can do one-time integration. You're gonna end over the time, you're gonna end up with the energy directly. But these are the formulas that we already discussed above. We're gonna use them here, right? Starting with the current, it is required to find the current. The current definitely should be C times dV by dt. He didn't ask anything regarding the charge. So I'm just interested in the current and the power. If we found the current, simply we're gonna multiply the current times the volt to give us the power. And if we did the integration from t0 to t, which is 0 to 5 seconds, as he mentioned down there, we can end up with the energy directly. Even there is no need to use these formulas, or you can use them, it's up to you. But let us use the integration form even. So if we consider this one more time here, for the energy, or let's say the current. So these formula, these are the equations that we have to plug in or use. For the current, it should be C dV of t by dt, right? Just write the equation to know exactly what you are seeking for. And the power, it should be the power of t, it should be the V of t times the I of t, the current. So once we find the current, we're gonna multiply the current times the volt. This is gonna give us the power. And the energy of t, it should be the integration from t0 to t to the power of t dt. We're gonna end up with this. So these are the three formulas that we have to use for solving this example. Make sense? But to do so, as you can see, everything depends on the volt, and the volt is already given as a discrete function, so we have to find the function, the discrete form of this graph, or graphically represented the voltage. So as you can see, it is like a straight line within the period from 0 to 1, and it is constant function within the period 1 to 3, and then it to have a declining straight line between the 3 and 5. It means that the slope of this line within this region, it should be positive, but the slope here, it should be negative, right? And it is just a constant function. So if we decided to write the function of this discrete system, or this discrete function, within the first period, which is from 0 to 1, it should be straight line. And if you remember that we said that the equation of the straight line, it should be like y equals ax plus b, where a, it should be the slope, and the b, it should be the y-intercept point, or the intersection point that is related to the intersection point of the line to the y-axis. So how we can find this function? Simply, the slope, it should be positive, a, it should be positive for this one, and here for this case we are representing v versus t, so it should be like at plus b. This should be the function, how it should be represented here, right? So the a, it should be the slope, and the slope, if you just calculate this triangular shape here, we said that the slope, it should be delta y, which is in this case, it will be delta v divided by delta t, which is like delta x. Delta t is just 1 second, delta v is 1000. So if you divide delta v by delta t, this is going to give us 1000 as a slope, and it should be positive. T plus b, it should be 0, because the intersection of this line, or this line, is going to intersect with the y-axis or the v-axis at 0 point. It means that it should be plus 0, where b should be in this case 0. So we're going to end up with this function. This is the line equation for within the period from 0 to 1 second. Make sense? This is for the time, the first one. The second one is very simple. It is just constant, so it should be 1000 within the period of t between 1 to 3 seconds. And then we do have this one declining. It means that the slope, it should be negative. In this case, we said that if the line is represented in the second and between the second and fourth quadrant, it means that it should have a negative slope. So initially the slope, it should be negative something, right? And let us do the same as we did for this one. So we're gonna have here delta v and delta x. Make sense? And delta t. Delta v, it should be 1000 again. Delta t should be 2, right? Which is the difference between 5 and 3. It should be 2, this distance. So 1000 over 2, this gives 500. And t, and remember that the slope is already negative. Then we are seeking a value for b. How much is b? Plus something here in terms, or negative something in terms of plus b. So if to calculate this b term, we can do a very simple calculation here. If we substitute for the time equals 0 within this function, it means that there should be some plus b within this region, right? We are seeking value for b. So if you plug t equals 0, t equals 5 into this equation, the value of the voltage should be 0, right? At t equals 5, how much is the value of the voltage should be 0. For example, at t equals 3, how much is the voltage is 1000. At t equals 4, it's going to be like 500. At t equals 5, it should be 0. So it means that the volt, I'm going to do a little bit calculation here to this one. The volt that it should be 0 at t, or in other words, to be more accurate, just to write this one, when the volt at t equals 5, it should be 0, which it should equal to the negative 5000 times 5. Or let us write the equation here. It should be negative 500 times 5 plus b. So how much it should be? B, then it should be positive of 2500, right? This should be the value for b, and this is what we're gonna use here. So definitely we end up with that b, it should be positive. This value, which is 2500, this is gonna give us the third equation in case that the time is already between 3 to 5 seconds, as already given up there, right? All right, so now let us move to the current. The current, it should be, once we found the V of t, we have to find the current, the power, and the energy. The current simply, the current function should be C, and C we got it by 10 negative 5. It should be 10 times 10 negative 6, so it gives 10 power to the power negative 5 farad. And if you substitute, it means that this C, in this case, C, it should be equals the 10 to the power negative 5 farad. And we have to do derivative for the voltage function first to come up with the current. Then if we multiply the current times the volt, this is going to give us the power. Then if we did the integration of the power over time, this is going to give us the energy function, and this is what we're going to do. So for the current simply, it's going to be the current I of t. It should be the multiplication. If you multiply 10 to the negative 5 times all of these values, and do the derivative of the first term, which is 1000 t with respect to the time, its derivative will be 1000 times 10 negative 5. This gives 10 negative 2, right? So the first term will be 10 to the power negative 2. This is within the time period from 0 to 1. And here the 1000, the derivative of this term simply is 0. So 0 times 10 negative 5 gives 0. So the second value will be 0. The third value, simply, this one, it should be, if we did the derivative with respect to the time, I can consider the 500, as we mentioned, that it is a common factor. So this is going to give us like negative t plus 5. The time derivative of this value, this is going to give us negative, or simply from here, this time derivative here will be 0 this time. Here we're just going to end up with negative 500 times 10 to the power negative 5. This is going to give us the negative 5 times to the negative 3, and this is when within the time period from 0 to 1, and this is from within the time period from 1 to 3, and this is within the time period from 3 to 5. Make sense? So this is for the current. We got the current. Simply what you're going to do next is just to do multiplication of the current times the volt to end up with the power, right? So your objective is just to multiply 10 to the power negative 2 times 1000 t. This is going to give us the function of the power. So simply the power p of t, it should be this function, 10 to the negative 2 times 1000 t. This gives at the end 10 times t. Within the first period, 0 times anything here, it should be 0. So this function, it should be 0. And the negative 5 times to the negative 3 times this value, times this function. So let us consider this function, this linear function with this form. So you're going to do the multiplication of the 500, which is a common factor, times the negative 5. So it's going to be times negative 3. This times 500 gives at the end 2.5, but it should be negative, right? Because this is already negative here. So this is going to give us negative 2.5 times the negative t plus 5, right? If you just did the multiplication, you're going to end up with this value. This should be within the time range between 0 to 1. And here from 1 to 3. And this one, it should be between 3 to 5. All right, so this is for the power. The energy, it is a little bit tricky here. But because, why? Because we said that before, that the energy should be the integration. As he mentioned, that we would like to calculate the energy within the time period from 0 to 5. So we have to do the integration. This is what we conventionally do. We do the integration over the time period from 0 to 5 to the power dt, right? But if we did this integration gives us value. A value, it means that we're gonna get the total power. We're gonna get the total energy stored in the capacitor. If we did the integration and we consider the limits of the integration, we're going to end up with a value of the power. This is going to give us the total energy of the energy. I'm sorry. This we're going to give us the total energy stored in the capacitor, right? If we consider the limits of the integration. But here, and if we did so and we consider the limits, we're going to end up with the energy as a value. And the value, it will be represented in the plot or the figure as a point. So, but here he asks us to plot the energy. He asks to find and plot the functions of the energy stored within the time period between 0 to 5. It means that for the energy calculation, so we can calculate the energy, we have to do the integration without the limits. Just do the integration of the power over the time without plugging the limits of the integration. So we're going to end up with the energy as functions. Then we can plot these functions as we're going to do for the current, typically the same like the current and the power. And this is what we're going to do. So we're going to consider here the energy. It should be, your objective is just to do integration to these three functions. So what is the integration of this one? It should be simply as t squared, 10t squared, and the integration of this one is simply still 0 because the integration of anything is just 0. Or basically this should be like constant. To be more accurate, the integration of the power within this period, it should be constant in this way, right? So it is constant. Why it is constant? If you remember, because basically what is the derivative of any number? What is the derivative of any value? Of any constant value? It should be its derivative with respect to the time should give us 0, right? So it means that this 0, and here we are doing integration. Here we are doing integration. The integration of the 0 with respect to the time, it is not necessary to give us 0. It would be 0 or it would be generally any constant value. Why? Because if you did derivative to the constant, this is going to give us 0. Like the derivative of c with respect to the time equals 0, right? To switch the integral, you have to do derivative to both sides, right? So, or to get rid of the integral kind of, you have to do derivative to the both sides. So the derivative of the constant gives us 0. So the 0, it means that the integral of the 0 here, it means that we should have a constant value for the energy within the second period, right? This constant value would be 0, would be any other value we don't know yet. So it's just a value for now, just any constant c. Make sense? So this is for the energy within the second period, it's just constant. Then within the third period, you're going to do the integration. The integration, you're just going to add one exponent here over this one, add to the exponent 1 and divide by the new exponent and divide by the derivative of what is inside the parentheses. So we're going to end up here with negative 2.5 times, this is just a constant, times the negative t plus 5, then you're going to add 1 to the exponent and divide by the new exponent times the derivative of the term that is inside the parentheses. The derivative of negative t gives negative 1, the derivative of 5 gives 0, right? So we're just going to end up with this expression. This is going to give us the energy. We can simplify this function or consider just divide by 2 the 2.5, and you can get rid of the negative 1 with the negative here. So we're going to end up, this expression can be written as 1.25. This is half of the 2.5, and it's going to be positive times the negative t plus 5 squared. Make sense? Then this should be within the time period between 0 to 1, and this should be within the time. I'm talking about the constant between 1 to 3. And this should be within the time constant between 3 to 5. Make sense? Then our objective now, we got these three functions, the current, the power, and the energy. We have to plot these three functions here, right? So let us start with the current. So I'm going to consider this is the vertical axis for the current. I of t. And I'm going to have this is the horizontal axis for the time in terms of seconds, and the current definitely it will be in amperes, right? And your objective is just to draw these functions. So simply to plot the function, it is very simple thing. Why? What you're going to do here for the time periods the time is already split over 3 periods, which is from 0 to 1, 1 to 3, and 3 to 5, right? So your objective is just to calculate the functions of the current, these three functions of the current at these 3 time periods. So for example, if you substitute for the time in this function equals 0, this is going to give us 10 to the power negative 2. If you substitute with equals 1, it's going to give us the same function. Why? Because all of these are constant functions. So the current will be represented as constant function with this value within this time period and 0 within this time period, which is 1 to 3, and within 3 to 5, it should be negative 5 times to the negative power 3, right? So it means that the current will be simply represented as a constant function within this period, 1 to 2, 0 to 1, and 0 within 0 function within 1 to 3, and it should be negative 5 here. It should be negative up to negative 5 within 3 to 5. So what does it mean if we just represented this line? So the value here, it should be 10 to the negative 2, and the value of this function, it should be here the 5 or the negative 5 to the times 10 to the power negative 3. Make sense? Then your objective is just to connect these functions, all of them together. So this is gonna give us kind of like the current within this period. Here it should be 0. The current within this period is just constant as well within this period from 0 to 1. Make sense? So this is the current function, which is very simple, similar to the previous example. Now we're gonna move to the power function. So this is the power axis, and this should be the time axis. And we're gonna break the time also into 3 periods from 0 to 1, 1 to 3, and 3 to 5, as already represented here. And this should be the power. And as you know, the power, it should be measured in watts, and the time definitely it will be in seconds, as already given up there. For the power function, as you can see, they are linear functions. This is a linear function or a function of a line. This is a constant function equals 0, which is very simple function. This also is a linear function. So your objective is just to draw a line, but you want to draw a line or to plot this function is gonna be much more simple, very simple. How? Your objective is just to plug the time once equals 0, once equal 1 into this function. So you're gonna end up with 2 points. Then you're gonna connect these 2 points with a line. Very simple thing, right? So don't care about the slope, is it positive, negative, these kind of things, don't care about it. Your objective is just to locate 2 points within this time period and connect these 2 points together with a straight line, since this one is a linear function. Very simple. So the first function is 10t. If you substitute for the time equals 0, this is going to give us 0. So the first point here over this axis, it should be 0. When t equals 0, the power, it should be 0. The same thing, when t equals 1, the power, it should be 10. Substitute y, 0 and 1, because these are the time periods, right? These are the limits of the time period. So if you plug t equals 1, this is going to give us 10 watt as a power. So when t equals 1, the power, it should be 10. Makes sense? The power, it should be 10. Then what? So this is for the first period. So we got 2 points. Your objective is just to connect them with a line, and that's it. So this is gonna give us the first function within the power within the first period. How about the second period? It is 0. So it is simply 0. 0, it means that it is constant function. So within the period from 1 to 3, the power is already 0. Even you can connect this point to this point to have one graph, like one curve, right? It means that here we're gonna have a abrupt change in the power from being 10 watt, it will be suddenly dropped to the 0 within the time period between 1 to 3. Then something is gonna happen to the power within the period from 3 to 5 as based on this function here. If we expanded this function just do the multiplication of the 2.5, we're gonna end up with 2.5 or even there is no need to. If you did the multiplication, you're gonna find that t is positive. It means that it should be with a positive slope. But forget about this slope again. As usual, block t equals 3 once and t equals 5 once. So if we substitute for t equals 3 within this function, so it's gonna be negative 3 plus 5 times the negative of 2.5. This is gonna give us negative 5. So the power when t equals 3, it should be negative 5. So the power when t equals 3, it should be negative 5. It means that I have dropped down here till the negative 5 at this point. It means that if we just extended this line, this value here, it should be the negative 5. Make sense? So this is going to give us the first point. How about the second point? Your objective is just to block t equals 5 into this function. So negative 5 plus 5 gives 0. So it means that the power at t equals 5, it should be 0. So we end up with these 2 points. Your objective is just to connect them with a straight line. Why straight line? Because this is a linear function as represented for the power function. So we're gonna end up with this graph for the power, that the power within the period between 1 to 0, it should 1 to 3 should be 0, but within the period from 0 to 1 it should be increasing up to 10, and here within the third period it should be decreasing up to the from positive to a negative power. Negative power, and we're gonna explain what does it mean a negative power just in a minute. So, but now let us draw the energy function. The energy function, it is higher order function. It is quadratic function here, quadratic function here, but it is a constant function with a certain value within the second period. So for this, since I don't know how much is this value, I'm gonna skip this one to the last. It means that I'm gonna plot these two curves first, then I'm gonna draw this one at the end. So starting with the 10 to the power 2, it means that this is a quadratic function. If you remember from the mathematics class, in case that we don't have a quadratic function, we used to represent this function into this form with like a U shape, right? And this U shape, it would be open up or it would be open down, like the green curve, right? This, in case that the coefficient, if we do have a function like a t squared plus other terms, in case that the a is negative, so it should be open down. But in case that in case that we have a function like a is positive, the a of the function, if it is positive, it means that it should be open up. This is simply how we represent the quadratic function. It should be like U shape, and this point is the vertex point of this function that depend on the other terms. So I won't gonna go deeply through these mathematical things, but the key point here, just to know exactly how it's gonna look like the curve, that for this energy function, it should be either open up or open down, depending on what, as I mentioned, depending on the coefficient of the t squared term of the quadratic function. Make sense? So we're gonna do the same thing that we did for the power, that we're gonna locate 2 points, but instead of connecting these 2 points with a line, we're gonna connect them with a curve. But the key idea, what is the direction of this curve? Is it gonna be looking open up or open down? This is the key point. Make sense? So given this, that again, in case that the a is positive, it should be open up, negative, it should be open down for the quadratic function. And this is the thing that we're going to use. It means that we're going to do the same as we mentioned, as we did for the power and the current. You're just going to look at 2 points and you're just going to connect between them with a curve and make sure that the curve, it would be open up or down depending on the sign of the coefficient of the t square term in the quadratic function. And this is what we're going to do for the first term here. This quadratic function, the t squared term, it has a positive coefficient. It means that the curve, it should be open up. But forget about the curve for now and its direction, and let us look at the points for this case. So what does it mean? It means that you have to plug t equals 0 into this function once and 1 in this function. So let us prepare here the curves, the axes for this one. So we're going to have here, this is the W of T, this is the energy, and the energy, as you know, it should be measured in terms of joules, right? And the horizontal axis, it should be the time as usual, which is gonna be broken down into like 0, between 0 to 1 and 1 to 3, then 3 to 5, 3 periods as already given here. So in the first period, you're gonna block T equals 0, so this is gonna give us 0. So the first point is gonna be when T equals 0, the energy should be 0. Then when T equals 1, the energy is going to be 10. So this is going to give us the second point. It means that we're going to jump up to the 10. In this case, where this just be the 10 joules. The energy unit, it is commonly known by 10. So this is going to give us the second point. And your objective now is just to connect these 2 points. In case that this was a linear function, so you're going to connect with a straight line, but now we have to connect with a curve. Forget about the curve for now, and let us get on and see how about and represent the second curve. The second curve here, it should be represented, as we mentioned, that 1.25 times negative t plus 5 squared, right? So what does it mean? You're going to block once t equals 3 into this function. This is going to give us negative 3 plus 5 squared times the 1.25. This is going to give us 5 positive, right? So when t equals 3, we're going to have 5 Yeah, it should be here, yeah. Yeah, this should give 5, but it doesn't make sense since this should be like next to the 10. So there is something wrong here. Yeah. And I think this should be like divided by 2. There is missing here over 2. Right? Why? Because when we do the integration of this term, this should be 10t squared divided by 2. I forgot to divide by 2 here. It means that this value should be 5t squared over 2. So when we substitute for t equals 0, this is going to give us 0 the first point. The second point, it will be t equals 1. It should give us 5. So this value should be 5. All right? So this should be 5 here. Make sense? So if this is 5, and if we substitute for t equal 3 here, we're going to end up with 5 as well. It means that when t equal 3, we're going to end up with 5. Right? The same level when t equal 3. Then if you substitute for t equals 5, this is going to give us 0. Negative 5 plus 5 gives 0. So this term will be definitely 0. It means that we're going to end up with another point, and we have to connect these 2 points with a straight line. Not a straight line. It should be connected by a curve. But assume that we do have a virtual straight line here, and then we have to connect with a curve. But how about the function in the middle? It should be a constant function, right? And we didn't know how much is the value of this constant function, but now we got this value. Simply, if you connected these 2 points together, we're going to end up with a constant function. The value of this constant function C, it should be the 5 joules, as we already got it here. Make sense? But now we have to connect these 2 points over this one with a curve, these 2 points over this line with a curve, right? So how it's going to be the curve? We'd have 2 options for the curve by connecting these 2 lines. I can connect with a curve that goes up, goes in this direction. The other option that we may connect them with a curve that goes in this direction. So which one is correct? The red one is the correct one. Why? Because simply the green one, if you decided to complete the U shape, the green one, it will be represented in this way. So as you can see, the U shape is already looking down. But the red one, if you decided to complete the U shape, it will be looking up. So, or open down and open up. So which one? The one that I should use, the one that is open up. Why? Because within the first period, the t squared term in the energy function, it has a positive coefficient. It means that it should be open up. It means that the curve should be open in this direction. Make sense? The same thing for the third term. The third term, the coefficient of t squared, it should be positive. For example, if you expanded this term, let us expand this term. This is going to give us here 1.25 times t squared negative 10t positive 25, right? So the coefficient of t squared is positive. It means that also it should be open up. You got it? So what does it mean? It means that for both curves, the quadratic curve, it should be open up, and this is what we're going to do. So what does it mean? This means that the green curve is not correct. We have to use the green curve in case that the coefficient of t squared is negative, but here it is not negative, so I have to cancel this one. So we're gonna remove the green curve. It doesn't work for us, and just keep the red curve because its U shape, it is already open up as already given here. Make sense? So it means that we're just gonna use the curve, connect these 2 points with a curve in this way. How about the other 2 points? We'd have 2 options, either to connect this direction or connect the opposite direction, right? Both are curves and both are quadratic curves. There is no need to accurately represent a quadratic curve. Just connect with a curve, and you have to make sure that this curve, it should be a quadratic curve. But the green curve gives a U shape that is open down, which is not the case because the coefficient is positive here. It means that we have to proceed with the red curve because its U shape will be open up in this way. Make sense? So it means that the correct curve, it should be this one and this one, and we do have the constant function in the middle, and this at the end is going to give us the energy function as we represented it here. So this is for the current function, this is the power function, and this is the energy function over time, how it changes. If we are interested in the total energy, energy equals the area below the W of t curve plot. So as you can see, if you just calculated this area of this shape plus the area of this rectangular shape plus this area, and you sum all of these areas together, you're gonna end up with the total energy, because this area underneath the curve or below the curve, it should be the area that represents the integration of the W of t function over time from 0 to 5. But here we were interested in representing the energy as a function of the time over this plot, and this is what we did, and this is the requirement for this problem. Make sense? So this is for this example again, which is an exercise, another example on the capacitance and how it would be used, and the volt and the power and energy in relation to the current over the capacitor. So this is the second example. Now we're gonna move to the to another topic here, is to how we calculate the equivalent of set of capacitors. Like we do have these three capacitors already arranged that they are parallel. So these are parallel capacitor. So how about if I decided to combine all of them, or to come up with an equivalent electrical circuit that is just one capacitor here? See, that is fine even to represent the capacitor, by the way, as just two straight lines or one line and a curve, it doesn't matter. So I'm seeking a value for C equivalent. This is typically the same thing that we did before for the equivalent resistance. Like you do have set of resistors that they were parallel, and we would like to end up with the equivalent resistance of this one. So if we apply the Kirchhoff current law at these different nodes, at node 1 and node 2, and you're gonna realize that even, this is what we mentioned, that the voltage over this branch, it should equal to the volt over this branch, it should equal to the volt over this branch, it should equal to V, which is the total volt that comes from the source, right? Since they already parallel. If we apply that this condition that the volt is equivalent or the same over all of them, and then we applied Kirchhoff current law, we're gonna end up with, and we did some manipulations here, some calculation. I won't gonna go over these calculations in more detail, because anyway we're gonna reconsider this one again, and you can easily understand this equation. You simply, the current over this branch, it should be C1 times the derivative of the volt, which should be the same, because the volt here is the same like this one, like this one. So the dV by dt, dV by dt, dV by dt over the three capacitors is the same, but these three capacitors, they do have different capacitances, and we do have I1, I2, I3. The currents over these three capacitors are different. Then if we apply the Kirchhoff current law, we're gonna end up with this equation. As you can see, this dV by dt is a common factor, right? Is a constant that can be considered as a common factor. So we're going to end up with 1 plus C1 plus C2 plus C3 equal the dV by dt, which gives us the same equation of the current law. If I ask you to calculate or find the relation between the current and the C equivalent over this is the current I of t over this electrical circuit. So you're going to say that the I equals the C equivalent times the dV by dt, right? This is the equation, Kirchhoff voltage law, to this electrical circuit. So it's going to be the same, which we already got it here, like 1 equals some C times dV by dt. This C definitely should be the C equivalent. This is the equivalent resistance. So as you can see, the equivalent capacitance. So the equivalent capacitance equals the sum of the capacitance of all the three capacitors that were already represented or arranged over parallel. As you can see that this expression somehow is the opposite or is different than the one of the calculation of the equivalent resistance. And the equivalent resistance, if they were parallel, we were using a different formula. But we were using the sum of the capacitors in case that they were arranged in series. So as you can see that the parallel capacitors, they are equivalent to the series resistors, kind of. Make sense? It means that if you do have 3 or more capacitors that they are arranged in parallel, so in their case you can combine all of them into one equivalent capacitance. This equivalent capacitance should be the sum of all of these capacitances. Make sense? So this is in case that they are parallel. The opposite is gonna be in case that they already in series. So this is the parallel case. Okay, it seems that, yeah, this is in series. When they are already located in series, If we apply the Kirchhoff voltage law over this electrical circuit, and I'm going to give you an example in this case how we can apply Kirchhoff voltage law for multiple capacitances. But anyway, we can combine all of these capacitors into just one capacitance or one capacitor, that we're going to end up with an equivalent electrical circuit with a volt. This is the voltage source, and we do have C equivalent here, and there should be current here as I, already roaming within this loop. So how much is C equivalent in case that they already are in series? If we applied Kirchhoff voltage law, we're going to end up with some integral relations. And as you can see, this I1, I2, I3, they should be the same, because the current over these three capacitors, it should be the same as we discussed even from the resistive circuits. So it means that this integral term is common between these three terms, so we can consider this one as a common factor. So we can end up with 1 over C1, or 1 over C2, 1 over C3, which should give us 1 over the C equivalent. So we're going to end up that the C equivalent is going to be the 1 over the 1 plus 1 over C1 plus 1 over C2 plus 1 over C3 and so on. It depends on how many capacitors already arranged in series in this way. This is very similar expression to the equivalent resistance of parallel resistors. So as you can see, the resistance here is the opposite to the capacitance. It means that the series capacitors, they work like parallel resistors. The same thing, the parallel resistor or the series resistor, they work like parallel capacitors. So we do have opposite things here. Make sense? So this is simply how we can, it's going to be the same, but you have to consider the difference between being capacitor or being resistor for the calculation of the equivalent resistance or equivalent capacitance of these capacitors. Make sense? What I'm going to do now, and this is going to be the last thing for the capacitance topic, I'm going to solve this example, and the objective here is to find the voltage over V3 over the capacitance 40 millifarad. This M stands for millifarad. It means that this exact value, this value, for example, it should be like 30 times 10 to the power negative 3 farad, and this value should be the 20 times the 10 to the power negative 3 farad. Make sense? The same thing, this one, it should be the 20 times to the negative 3 farad, and this value should be the 40 times to the 10 negative 3 farad. Make sense? And the voltage source is already given by 30 voltage. It is required to calculate the current, the total current through over the source, in addition to the voltage V3, how much it is. So to solve this equation, let us, for example, as I mentioned, let us that we are interested in finding how much is V3, which is the voltage over this capacitor or even this capacitor, because you should understand that in case that we do have two parallel electrical elements, wherever they are, resistors, capacitors, even inductors, they should have the same voltage, right? So how much is V3, how much is V2, how much is V1, or basically let us just find it is required to find V3, how much it is. Also, let us investigate the total current I that should be through the voltage or this parallel, how much it is. Kind of like, let us investigate, and also how much of a charge that this parallel is going to give. This is what we are interested with. So, how we can solve this one? We explained chapter 2, 4 different methods of doing analysis for electrical circuits, but the focus was over the resistor circuits. The same 4 methods can be applied to any electrical circuit, whatever it is, whatever it includes resistors, capacitors, inductors, or combination between all of these different electrical elements. No matter what is this electrical circuit, we can apply any one of these 4 methods are applicable to any electrical circuit, whatever it is. Make sense? So for now, since we're already talking about the equivalent resistance and the equivalent capacitance, it means that it is, let us consider the second method, which is the equivalent capacitance method here. There it was the equivalent resistance method. Now we're going to work over the equivalent capacitance method to do analysis for this electrical circuit. So it means that the first step, as we used to do, It's just to try to distribute the current through the electrical circuit, assuming like there is like kind of current that should be roaming through this electrical circuit. So there should be like the total current I, and this current is gonna keep roaming as it is till this node. This is gonna be like node 1, right? And at node 1, this current is gonna be split into like I1, and there should be over this branch I2. Make sense? In this way. So this is the current distribution. Then after the current distribution, your objective is just to calculate the equivalent capacitance. In this case, we have so many capacitors here. These two capacitors, the 40 and the 20, they are definitely parallel. Why? Because the current has been distributed or divided over them. It means that they are parallel. So I'm gonna combine these two. Since they already parallel, we can combine these two as two parallel capacitors. These are two parallel capacitors, right? So we can combine them into just one C equivalent one. One C equivalent one is gonna be the sum, because according as we mentioned, the parallel capacitor, you're gonna sum their capacitance. So this is gonna be the 20 plus the 40. It's gonna give us at the end 60 millifarad. Make sense? And the millirad is 10 to the power negative 3 as we mentioned. So what does it mean? It means that we can redraw again this electrical circuit into this form. Like we're gonna end up with just 3 capacitors. We combine 2 of them into one, which is this one had been combined into C equivalent. This is the C equivalent one, and we're gonna have here the electrical source, which is a voltage source, positive and negative Vs, and Vs is already given here by 30 volts. And we do have here 20 microfarad, and we do have here the 30 microfarad, and we do have this equivalent we got it by 60 microfarad. Make sense? And the current in this case, it should be the same current that's roaming over all of these electrical elements. So what does it mean? It means that this current I of t, it should be the same current over this element. It means that all of these capacitors should be in series. So since they are in series, we're gonna calculate one C equivalent, which is gonna be the overall equivalent resistance to this electrical circuit. Is gonna be the equivalent of these 3 capacitors that they already located in series. And if you remember, we said that this C equivalent, it should be 1 over the first capacitance, which is 20, plus 1 over the second capacitance, which is 30, plus over the third one, which is 60. If we did the calculations, we're gonna end up with 10 microfarad. So this should be the equivalent capacitance to all of these capacitors together. So by this, we have simplified the electrical circuit into just one source, Vs, and one capacitance, which is the C equivalent that we already got by 10 microohms. And there is one current, which is I of t, is already roaming within this electrical circuit. Make sense? So simply we got the volt, or the voltage already given here by 30 volts, and we already have the C equivalent, which is 10 microohms. If I ask you to apply the Kirchhoff voltage law to this electrical circuit, we're gonna end up that the current I of t, it should equal to the C equivalent times the dV by dt, right? This is the current equation for a capacitor, right? This is the current that over the capacitor, it should equal to the voltage over this capacitor, which it should be the Vs, which is 30 volt, divided by a time derivative of this volt times the C equivalent, right? Or the capacitance of this capacitor. This is the current equation that we explained above in the start of this video. So simply given this, the C equivalent we got it by 10 microohms, but how about the time derivative of the volt of this voltage source? This voltage source gives DC voltage, and we mentioned once before, in case that we have DC voltage, so there is no current. The current definitely will be 0. So simply from this equation, we're gonna end up that the current within this electrical circuit will be 0. So what does it mean that the current within this electrical circuit is equal to 0? The current equals 0, this means that this battery, this source, which is a battery, this battery will be used for charging this capacitor, just charging the capacitor. Like you're gonna deal with this capacitor like your cell phone, and it's gonna take the charge from the battery, kind of. You got my point? This is how it works. There is no current, but there is a charge. And what is the charge? And that's why the charge here is required, right? So let us calculate the charge. The charge, the equation from chapter 1 even, the charge, it should be the integration of the current over time, right? Plus Q0 in case that you already integrated from 0 to t and there is initial charge in the capacitor, right? So here he didn't give anything about the initial charge in the capacitor, so it means that Q0 should be 0. We're gonna assume that it is 0 and we are interested in the charge, how much it is. So the charge definitely it's gonna be from here, we're gonna conclude that the charge is the time integral from 0 to t to the time which is already 0, dt. Make sense? If you remember, as we discussed in the previous example up there, that the integration of a 0, it gives a constant value. It gives a constant value, right? So the integration of the current, which is 0, gives a constant, but how much is this constant? We have no clue. So what does it mean? It means that this battery, since it is DC voltage, delivers a constant charge to the capacitor over time. Like all the time it sends like pulses, like charges. And the rate of sending this charge is constant. All the time, over a certain period of time, it sends the same amount of a charge. So we're gonna say that the charge Q, it is constant value, but we are interested of this value, how much it is. So how we can find the charge value? We do have another expression. This is the current. But you should understand, and this is if we go back here to the summary up there, we mentioned that the charge, it is related to the voltage through this equation, like Q equals C times V. So going back again to this electrical circuit down here, to this one, this is the electrical circuit that we are considering. So from this one, we're gonna conclude that the Q, which is the charge, it should equal to the C, which is here, it is the C equivalent times the volt, which is the 30 volts, right? So this is gonna give us equals, the C equivalent, we got it by 10 microfarad, so it should be times 10 negative 3 to convert from milli to farad, times the volt, which is already the volt of the source, Vs, which is already given by 30 volts. If we did the multiplications, we're gonna end up with the charge. The charge here, it will be 10 times negative 2, so it will be 0.3. So we're gonna end up with a charge of 0.3 coulombs, right? This C stands for the coulombs, and this C is just constant. This C here, it is constant, but this one refers to the coulombs, which is the unit of the charge. Make sense? So it means that this charge or this battery is gonna send a constant charge to the capacitor. This constant charge equals 0.3 coulombs over the time. It is a constant rate of the charge. Make sense? So we got the charge, we got the current as already required there. The current simply is 0, the charge, we already got it by 0.3. How about V3, which is the voltage over this capacitor? The voltage over this capacitor, the 40, it should equal to the voltage over this capacitor, the 20. It should equal to the same volt, the volt over their equivalent, which is C equivalent 1. So for example, the voltage here over this one is V1 as already given here. Over this capacitor is V2 as already given here. Over this C equivalent, it should be V3. So how much is V3? So how much is V3? Simply, it would be like very similar. Like if I ask you how much is the voltage over this capacitor, you can find this volt in terms of the current or in terms of the charge over this capacitor. For example, going back to the summary up there, we mentioned that the volt, we do have this expression, like the volt over a capacitor, it would be 1 over C, the integration of the current, dt plus V0. Assume that there is no initial charge in the capacitor, so V0 is going to be 0. Or you can directly find the volt by the Q as Q over C from this expression, right? So we do have two expressions here that we can use, either one of them, to find the voltage, right? In the equation down, the current was 0. And even the integration of the current, it gave us the charge. So both they are the same functions, kind of, right? So it is better, it is easy for us to find the volt as Q over C. So if I ask you, generally, if I ask you how much is the volt for this expression, Yeah, for this electrical circuit, how much is V3? It should be Q, which is the charge over this capacitor divided by C equivalent, right? By the C of this capacitor. So how much is the charge here? We got the charge, and you should understand the charge works like the current. The current over all of these capacitors is the same. So the charge over all of these capacitors is the same, and the charge, we already got it by 0.3 coulombs. So what does it mean? It means that V3, it should equal to the charge, which is the same over all the capacitors, divided by the C equivalent one, which is this, the capacitance of the equivalent capacitor. This is going to give us 0.3. We got C equivalent up there by 60 microfarad, right? So you're going to divide by 60 times 10 to the negative 3. If we did the calculation, this should give us the volt over the capacitor, or V3, which it should be in terms of volts, which is going to be 0.3 divided by 60 divided by the 10 negative 3. This is going to give us 5 volts. So what does it mean? This means that the voltage over this capacitor equals 5 volts, and the voltage over this capacitor will be 5 volts. The same thing, the voltage over their equivalent is also 5 volts. Make sense? If we are interested in the voltage over V2 or V1, we can do the same. V1 definitely, V1 it will be Q over 20, but V2 it will be the Q over the 30. Very simple. If you sum all of these three voltages, V1, V2, V3, it should give us the 30 according to the Kirchhoff voltage law. Because if we applied Kirchhoff voltage law to this electrical circuit, the sum of these voltages should equal to the input voltage. Make sense? So this is for this example to understand more what does it mean current, what does it mean charge and voltage for capacitors. And as you can see, we didn't, in terms of the electrical circuit analysis, we didn't do anything new except the expression that we are using for, or the relation between the current, the charge and the voltage for the capacitor. For this electrical circuit, there is no current as we mentioned. This means that this battery, it will be used just for charging all of these capacitors. Like assume that you're already using one charger to charge multiple cell phones. So these cell phones, their batteries will take the charge from the total battery or the input main battery source, which is this one, and they're gonna be charged and that's it. Make sense? This is for this example on the capacitors in parallel and series. The last thing that I'd like to mention here is that the real capacitors, as we discussed there, that the capacitor, it has a capacitance C. And this capacitance, this is like a measure of the capability of the capacitor to store energy. How much of energy that can be stored within a specific capacitor. This is the capacitance kind of, right? But there are some other effects. One of the effects or other things, one of these effects is known as the parasitic effect. What is the parasitic effect? This is basically the capacitor. It is not just a capacitor. It works like a capacitor and it includes some resistance and also includes some inductance. We said that the main three types of controllers that would be used for controlling the voltage and the current through the electrical circuit are three things: resistor, capacitor, and inductor, right? So if we gonna look to the capacitor itself, the capacitor should be made of metal. As we discussed in the previous meeting, the capacitor, it has like two plates, metallic plates, and there is a dielectric material in the middle between them, right? And if you remember in chapter 1, we said that any material, whatever it is, it has a resistance for the charges or the electrons to pass through the material, right? So for the capacitor, there are two plates, and these two plates are made of metals. Metals is commonly known that they do have lower resistance for electricity. They are good electrical conductor. Their resistance is too small, but anyway, they do have a resistance. So what does it mean? Physically speaking, or generally speaking, that the capacitor itself, it has a resistance. In addition, that it is already have a capacitance. In addition, it has electric field that some magnetic field would show up between the polarity because of the difference in the polarity between the charges over the first metal plate and the charge over the second metal plate. This would, in addition to the dielectric material, this would result in some magnetic field. electricity with magnetic field, this gives inductance, as we are going to discuss inductance. So inductance, it depends on electrical field plus magnetic field, or the interaction between two fields. One is magnetic field, the second one is electric field. Field like a force, kind of. Okay? So the exact or the real capacitor, it should have some resistance, it should have some inductance, as already represented here. So we're gonna have one resistance that is gonna be in series, one other resistance that is gonna be in parallel to the capacitor itself, and in addition to the inductance. This is a representation of the real capacitor. So what does it mean? As we represented up, we said that the capacitor, it has like one plate, and there is another plate, and there is some dielectric material in between, right? So let us figure out the trip of one electron through these different materials. So this electron the electron comes through a wire, right? This is the electrical wire, and there is another wire, and this should be the capacitor, right? So let us just pick one electron. This electron is gonna keep going in this direction. So it's gonna go through the metal. This metal itself, it has resistance R, right? In addition, it's gonna go through this dielectric material. It has another resistance R. In addition, there would be some magnetic field that would be generated over the electron itself. This magnetic field, there are some magnetic field would show up or generated that it will affect the movement of the electron. So the electron moving under resistance of the metal, under resistance of the dielectric material, under a magnetic field that generated because of the difference in the polarity and the material type and the dielectric material. These things, all of them together, generate a specific magnetic field. Okay? It means that the electron will be moving under the influence of a magnetic field. In addition, that it is being electrical field. And then when it goes through the second metal plate, it has another resistance, and then it's going to go through the wire. So as you can see, there are resistances acting over this or overcome the flow or the movement of the electron, in addition to some other magnetic fields. So the capacitor itself, it cannot be purely capacitor. The pure capacitor, the ideal capacitor, it doesn't exist. Because anyway, there are some resistance, there are some magnetic field that would show up because of some other physical phenomena that act on the electron while it moves between the two plates of the capacitor. This is known as the parasitic effect. But this parasitic effect is very negligible, is very small in many of the cases, because we are using these plates are made of metals. So the resistance of the plates are very negligible, and that is fine to disregard that there is a resistance inside the capacitor itself. The same thing for the magnetic field. The magnetic field that is generated, it is likely to be very small magnetic field, and that's why it can be neglected. But if we decided for some application, it is highly important to consider this very small resistance, to consider this very small magnetic field, and in this case, the capacitor, the exact capacitor, it will be represented by two resistances in addition to one inductance, in addition for sure to the capacitance of the capacitor itself. This first resistance is known as series resistance. This is the resistance of the capacitor plate material. This resistance show up because of the resistance of the metallic plates of the capacitor. And in addition, we do have LS, which stands L. This is the inductance of the inductor. And this comes because of the magnetic field. As we said, there would be some magnetic field show up or acting on the electron while it moves through the capacitor. So this magnetic field will result in some inductance effect. And that's why we can represent this thing into the form of inductor. And we're going to discuss the inductance after this video. Okay? But in addition to this resistance and inductance, we do have resistance. This better resistance, this is the conductance of the dielectric material. Or in other words, this resistance, it depends on the dielectric material itself, or it is related to the dielectric material, because we have to make the dielectric material to be like the material that not allowing for electricity to pass through, right? But this dielectric material, it means that it should be like a completely isolating material. Isolator material, it should have, it has resistance that tends to infinity. But we cannot reach the infinity. There is no resistance that is infinity. Anyway, any dielectric material, it will have a specific resistance that would be huge. It means that it will have some conductivity, that it can allow for a few electrons to pass through the dielectric material. So the conductivity, that's why we say that this is the better resistance, that due to that accounts for the conductivity or the conductance of the dielectric material, or the ability of the dielectric material to let current to pass through. Because the dielectric material should be isolating material, there is no current. It means that the current through this dielectric material should be completely zero. But this is an ideal case. There is no dielectric material that can give us 100% zero current. Anyway, there should be some current. There should be some leakage in the current. It means that the allowance or the ability, or because the dielectric material would let or allow a few current, very few current to pass through it, this means that it has resistance that is not infinity, and that's why the conductance of this dielectric material, it should be represented as parallel resistance to the capacitor. So this is an ideal, this is not ideal, this is the exact model of any capacitor. But as we said, this R, this LS, this RP, all of these other resistances and inductors, their effect are very negligible. These capacitor, these other effects, the magnetic field, the resistance of the dielectric material, the resistance of the metallic material, these are all together known as the parasitic effects. And these parasitic effects are very negligible in many of the application of the capacitance, right? But in a few application, in some specific application, this parasitic effect is a big deal, and there are lots of research regarding this area for the parasitic effect on the capacitor, that researchers basically doing some research by studying this parasitic effect and harnessing this effect in some application. But this is not the interest of the practical use. In the practical use of the capacitor, we don't care about the resistance of their metallic plates or the inductance due to the magnetic field that would show up. But generally speaking, that you should understand that the capacitance or the capacitor, it has some resistance, it has some inductance as well. That makes sense? But they are very negligible, and this is what we're gonna assume through this class. All right? So this is for the capacitance and the capacitors, and this is gonna be the end of this video. So through this video and the previous one, we have discussed the capacitance and the capacitor, and we had examples on how we can relate the current, the volt, the charges together through the capacitor, in addition to calculate the power and the energy. Then we discussed the equivalent capacitance for parallel or series capacitors. In addition, we consider the exact model of the capacitor. All right, so that's it for this topic. The rest of the chapter is related to the inductance and inductors, so we shall repeat similar things that we already covered for the capacitors and capacitance. We're gonna cover them for the inductors. All right, so thank you and see you in the next video.